Okay, yesterday when we looked at vectors, I'll let that come to focus. Okay, when we looked at vectors yesterday, I gave an identity where I said vector A dot vector B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. So how did we arrive there? We can think of this as sort of a projection. So let's get two vectors, x and or A and B, on the x and y axis. This is y, this is x. We have vector A, and we have A is got a y coordinate. We'll call this y1, or let's call it y A, and we have an x component of this vector, we'll call xa, and this is 0. We're starting at 0. And we have another vector, B, and it has an x and y coordinate of its own, so we'll call this by, or b sub y, or y sub b, and we have an x component for that. We'll call that xb. Let's use the same notation, B, capital B. So we then write the vectors as A equals XA I plus YA J, and B is equal to XB I plus YB J. Well, we know the magnitude of A is equal to the square root, it's really the Pythagorean theorem, of XA squared plus YA squared, square root, and the magnitude of B, this is magnitude of B is equal to the square root of XB squared plus YB squared. And that's what this is. This is the hypotenuse, or the magnitude is of this vector is XB squared plus YB squared, and the magnitude of this vector is XA squared plus YA squared. So when we do the dot product, remember we were told that we're multiplying similar components. So when we go A dot B, we're going XA times XB plus, because I dot I equals 1. Remember, dot products give scalars. and we have y a times y b, and that's some scalar number n. But what if we had a divided by the magnitude of a? Well, that's equal to xa divided by the square root of xa squared plus ya squared I plus ya divided by the magnitude xa squared plus ya squared j. But that's also equal to, now let's say this is angle phi between b and the x-axis, and angle theta, which is the angle between angle A and B. So this is the angle of A to the x-axis, which is theta plus phi. So this is simply the cosine of theta plus phi I plus, and this component is sine theta plus phi j direction. And b, on the magnitude of b, is similarly xb on the magnitude of b on the I plus y sub b on the magnitude of b equals cosine phi I plus sine phi j. Now, what if we do the dot product at this point? So we have, again, we have a on the magnitude of a equals cosine of phi theta plus phi I plus sine theta plus phi j, and b on the magnitude of b is equal to sine of theta plus, oh, I'm sorry, it's just simply the, I'm thinking ahead without thinking. This is cosine of theta, or phi I plus sine phi j. So a dot b over the magnitude of a and the magnitude of b is equal to, we can bring those out because those are just numbers, magnitude of a, they're scalars, and magnitude of b times a dot b. And remember, when we do a dot b, we're multiplying components. So that this a dot b on a magnitude of a and b over the magnitude of b is equal to, now let's do this dot product. That is cosine phi times the cosine of theta plus phi not I, that's again that. And we have sine phi times sine theta plus phi. But we use our identities now. We're going to have to utilize space here. Okay, cosine phi times cos theta cos phi minus sine theta sine phi plus sine phi times sine theta cos phi plus sine theta sine phi. Sorry, I got a little mixed up there. Sine phi cos theta. And now all we have to do is multiply this whole thing out, and we have cosine squared phi cos theta minus cos theta sine phi plus sine theta cos, let's see, sine theta cosine phi cos phi plus sine squared phi cos theta. Now we see this and this are really the same, so they cancel out. And we're left with cosine squared phi plus sine squared phi times cos theta. But we recognize this identity as 1, so we're just left with A dot B over the magnitude of A and magnitude of B equals simply the cosine of the angle between the two vectors. Bring this back, we could see theta there. So this is how we arrive to this formula. I see it's struggling trying to keep the focus right there. Let's see if I can just maintain focus that way. All right, so then if we multiply this out, we have A dot B is really the magnitude of A times the magnitude of B times the cosine of theta, or it's equal to A, the magnitude of A, cos theta times the magnitude of B. Now we can think of this as the if we look at the vectors A and B and A, and we have the magnitude of A and we have the magnitude of B. We can think of this as being the projection of the magnitude onto the vector B, the magnitude of the vector B. So in a sense, it's the component of A that is in the direction of B, and how it amplifies B. They call that the projection of A, or the magnitude of A cos theta, which is the component of A that's in the same direction as B, onto the magnitude of B. So it's sort of an amplification when you think about of what a dot product is. And so I just wanted to let you have some conception of an idea of where that formula came from, because this formula I just gave it yesterday in a rush without any justification. So I just wanted you to know that there's a way to derive it. I hate giving formulas without derivations, and that it has some kind of a meaning, and that's what the meaning is. That you'll hear people call this the projection of A onto B. So I think that helps us understand a little bit of what a dot product is, and how we actually get to this point, starting from the basic definitions and a little bit of trigonometry, which we learned. I don't know why that thing is oscillating like that. There we go. So I just wanted you to see that, and the next videos we're gonna do some more vector problems, and we're also going to learn the cross product. The cross product, which basically is, we say A cross B. And what is that? That's equal to the magnitude of A and the magnitude of B times the sine of the angle between them plus a vector, because a cross product yields a vector. It doesn't yield a scalar like a dot product does. So it yields a scalar. This is another, when you put a little hat on something, that's another notation for a vector. So we'll take a look at that and how we get to this formula and what a cross product means and how you calculate it, because it's a little more complex in its and how you carry it out and how you find a cross product. So anyway, I hope you found this short video informative about a dot product, because I did not go into the definitions very deeply yesterday.